Okay, this video is on matrix row operations. These are operations that we perform on the rows of a matrix. Um, well, you should have downloaded and read over the reading, which is really just a list of the row operations that we will be using. We have 4 allowable row operations. And this video, the purpose of it is to just give you some examples of what those row operations look like when you're using them on the rows of a matrix. So we'll start with the simplest one, which is just to swap the position of the rows. So this matrix only has 2 rows. When we swap the positions of rows, we're going to use this notation. This is an R with the subscript 1 and an R with the subscript 2. And this is a double-headed arrow between them. That's not the nicest double-headed arrow I've ever written. So it's R sub 1 swapped with R sub 2. This is the information that tells me what I'm doing in this step. You will have open answer questions on the final, and you will be required to write out the steps just like that. So I'm swapping the position of these rows. So row 2, that had 216 in it, becomes row 1. So now row 1 is 216. Row 1, which says 435, becomes row 2. So I write 4, 3, 5 as row 2. That's really as simple as it could possibly get. We're just swapping the positions of things. I want to point out that because every row in a system like this one represents an equation, this, when we're talking about solving systems, is just akin to writing the equations down in a different order. This is definitely an allowable step. So let's go on to some more meaningful row operations. I mean, swapping positions is handy, but let's talk about some of the more active ones. So there are going to be times when I want to multiply a row by a non-zero constant. Let's point out that we're using these row operations in an attempt to get to our goal form that was covered in the previous video. So notice that almost everything on that coefficient side is perfect. I've got a 1 and a 0 and a 0 and a 1/2 here. This 1/2 wants to be a 1. The way that I can always reliably get a number to change into a 1 is by multiplying it by its reciprocal. So the reciprocal of 1/2 is 2. Now I can't just come in here and multiply a single number. I do have to multiply the entire row. So I'm going to show you how we're going to write that. It's 2 times row 2, and then we are going to recopy that as row 2. So I'm going to multiply row 2 times 2, and I'm going to store this result in row 2. I don't want to add rows to my matrix as I'm going, so we will always be replacing an existing row. So 2 times 0 is 0. 2 times 1/2 is 1. And 2 times 3 is 6. So there is that result. I do want to point out that this is essentially multiplying everything in the equation by a constant. And that's why I'm allowed to do it. So in this example, this original equation, this row represents the equation 0x plus 1/2 y equals 3. And I am allowed to multiply both sides of an equation by a constant, by a non-zero constant, and then distributing. Well, 2 times 0 is still 0. 2 times 1/2 is 1. Of course, I don't have to write that one, but I will for emphasis. And 3 times 2, of course, is 6, which is what I got when I multiplied the row. And let me emphasize, this works when you're multiplying by a non-zero constant. If you multiply by 0, then you are just wiping out one of your rows, and you do not want to do that. Another thing that I want to emphasize is that when I am replacing a row, it has to be the row that was used. Otherwise, I can't multiply row 2 by 2 and then put that in row 1. Otherwise, I'm obliterating all of the information that was in row 1. So now, let's talk about when the rows get to interact with one another. So when I get to add a row to another row, I'm going to rewrite my goal form again. That's 1s along the principal diagonal, 0s everywhere else, and the right-hand side is a column of constants. So notice again, I've got an almost perfect matrix, but this -1 wants to be a 0. So I can't get there by multiplication, because the only way to do that would be to multiply the entire row by 0, and that wipes everything out. That's no good. I need to get there by addition. So if I take row 1 and add it to row 2, then I can store that result in row 2, and that will give me my goal form. So 1 plus -1 is 0. 0 plus 1 is 1. And 5 plus 2 is 7. So let's look at why this works. This matrix is represented by the equation x plus 0y equals 5. And this row is represented by the equation -x plus y is equal to 2. So remember using the elimination technique to solve systems of equations. If I add these equations together, then x plus -x, well, that's 0, x, for emphasis. Then 0y plus y, well, that's 1y. And I think I am going to write the 1 in for emphasis. And 5 plus 2, that's 7. Notice that the equation that I end up with is equivalent to the row that I ended up with. So when I add rows together like this, I'm really just performing that elimination strategy of solving a system of equations. So now let's look at an example of our fourth and final row operation, where we multiply a row by a constant and add that result to another row. And again, I'll keep my goal form in mind. All right, so I want to change this 7 into a 0. That's the only thing that's not perfect as far as my goal form is concerned. I need to, I can't get there by multiplication because multiplying by 0 would get me that 0, but then everything would become 0, and that's not what I'm after. I don't want to obliterate the first row. So I need to get there by multiplication, by addition. However, if I just straight up add, I'm going to add 1 to 7 and then I'll have 8, and that is not what I want. I want a 0. So what I'm going to do is multiply row 2 by 7, but I don't want to actually change row 2. I want to leave row 2 the way it is. I'll multiply it by 7, keep that result in my head, and then I will add that to row 1. I'm going to store it in row 1. So, negative 7 times 0 is 0. 0 plus 1 is 1. So next, negative 7 times 1 is negative 7. Negative 7 plus 7 is 0. Negative 7 times 7 is negative 7. And then negative 7 plus 4 is negative 3. I just realized that the fact that that was a 1, maybe this was not the best example. Let's do an extra one of this type. So we'll have something similar. Then 0, 1, and 4. Okay. So now I'm going to do a very similar, well, it's the same process, different numbers. It's this 3 that I want to change. I want to get this 3 to be a 0. The way I get 3 to be a 0 is by adding negative 3. So negative 3 times row 2 plus row 1, and I'm going to store that in row 1. So negative 3 times 0 is 0, plus 1 is 1. Negative 3 times 1 is negative 3, plus 3 is 0. Negative 3 times 4 is negative 12, and negative 12 plus 10 is negative 2. Then I recopy my second row because that hasn't changed, and there is my system. So now let's look at why that works. This system of equations is 1x plus 3y equals 10, and 0x plus 1y equals 4. Now, this is not nicely set up for eliminating y's. And yes, of course, if you were just after solving this, you could easily solve it by substitution. But this is the purpose of this example is not to get an answer, but to build understanding of a larger process. So if I multiply both sides of this equation by negative 3, then I would have 0x minus 3y equals negative 12. And when I do my elimination now, I would have 1x. That cancels out. For emphasis, I'm going to write a 0y. And 10 minus 12 is negative 2. And so notice that this process has given me the same result as my row operation did in the first row. Once you get used to these row operations, they're a much faster way of solving systems of equations. The real advantage comes from the fact that it's easy to program computers to do this work for us, but we do want to have a strong understanding of what the row operations do and the process of solving a system of equations this way. So next, watch the video, Solving Systems of Linear Equations Using Matrices.